So in this first question, we have a Maxwell-Boltzmann distribution diagram. As you have known, energy on the x-axis and the number of molecules or the proportion of molecules with energy E. This is at a particular temperature T1. When you increase temperature to T2, so they've shown you something dotted. So the dotted line refers to increase in temperature. And we know that when we increase in temperature, we will change the molecular distribution energy. We will skew it meaning you shift it to the right hand side. So your activation energy doesn't change when you change temperature. So there must be T2, which is higher temperature. That's when you skew the graph to the right. The maximum proportion of molecules with that give energy decrease because overall you have more molecules that have higher energy. You increase the proportion effective collision. That's why the rate increases. Alright, so the graph must have skewed to the right, and the only one correct and sensible there is option D. So option B has not shifted the proportion effective collision because you have just raised the height. You have also raised the height here. But in terms of proportion effective collision means how much this area is compared to this area. Alright, whereas here you have just increased the total area under the graph, and that is not something that happens. When you increase temperature, you do not get more reacting molecules. Okay, T2 is actually here at a lower temperature, so it has skewed to the left, so that it becoming lower temperature. Whereas this one in C is skewed to the right, but you see the maximum has gone up. Instead of distributing the whole thing where you get more molecules with higher energy, you should have lesser molecules with that maximum peak there. Okay, if you have this graph, this means your total area under the graph has increased. And again, just like this previous option, your total area under the graph does not change when you change temperature because the area under the graph tells you the number of molecules, number of reacting molecules, which doesn't change when temperature changes. Next question is an energy profile diagram. So you have with and without a catalyst. So very clearly, if I just mark in brown here, brown is going to be the uncatalyzed, and this is also the uncatalyzed, whereas the green one refers to, what am I talking about? There's a lot of things here. Okay, maybe I just skip that again. They want the overall enthalpy change of the reactions. So from the reactants to the product, okay, from reactant to product, it should be a one-way headed arrow, just like what I've drawn. That is lesser than 0 because it's going downward. Your product have less energy than the reactant. Very clearly, C is the enthalpy change of reaction. So what I was trying to do just now is because we also have the forward reaction. If we just think about forward reaction, if you have the uncatalyzed, then you would have, uncatalyzed and the catalyzed. The enthalpy change is equal to option C, going downward. Okay, I don't know the actual value because we have not been given an actual value here, no absolute value. But the uncatalyzed activation energy from the reactants to the top of the peak, so that is option B. Whereas for the catalyzed one, your activation energy is going to be lower. There you go. So it's option A there. All right. So of course I can ask you about the reverse reaction as well, going from the reactant to going from product to the reactant. So this is the activation energy for the backward reaction, which is uncatalyzed, whereas C plus A is the activation energy for the backward reaction for the catalyzed reaction. Okay, and the enthalpy change will be equal and opposite to the one going from reactant to product. So this is going from product to reactant. It will have the same value as this, but it will have the opposite sign because it's going upward. Question 3. So we are advised to eat less than 6 grams of salt for obvious health reason. So what mass of sodium is present in 6 grams of sodium chloride? In the formula unit of sodium chloride, you have NaCl, and the mass, so this is, instead of working out the percentage mass, is mass of sodium. It's going to be, you have 1 sodium out of the molar mass, which is I think it's 23.0. So divided by 23.0 plus 35.5. Okay, and then you don't want to times, well, hang on, I want to times, okay, I want to times the 6 gram. Okay, so it's 23 divided by bracket 23 plus 35.5. So the bottom bit should give you 58.5. Don't forget you should use bracket to avoid calculation error. So 2.5897, 2.36 gram to 3 significant figure. Number 4, this is a classic copper plus corn nitric acid. So we know copper does not react with dilute nitric acid. If you remember from your GCSE, IGCSE or O-level, copper is below hydrogen in the reactivity series. They don't react with dilute acid. This is 50% solution of nitric acid. This is corn nitric acid. Copper does react with corn nitric acid to give you this reaction here, copper nitrate, water, as well as nitrogen monoxide. All right. So you can think of this, this is actually a redox reaction. So this is copper metal, which is copper 0. This is called copper 2 nitrate, where each nitrate is NO3 minus. You have 2 of it, so you have copper plus 2, which is copper 2 plus. Oxygen here is minus 2, nitrogen here is plus 2, because the overall molecule has no charge. In the NO3 minus, which is the same as that, you can see it's a minus 1 equal to nitrogen plus 3 times minus 2 for the oxygen. Nitrogen is minus 1 plus 6. Nitrogen is plus 5. So what we have there really is a redox reaction, where this copper 0 goes to copper plus 2. So this is a change of plus 2. And you have that plus 5 going to plus 2. That is a change of minus 3. But of course, you also have the nitrate staying as the nitrate. So here there's no change going from here to here because the nitrate is still the nitrate, but some of the nitrogen actually does get reduced, decrease in oxidation number to form NO. So with this kind of question, you can choose to, because it's a redox equation, you can choose to balance this equation by using changes in oxidation number, which can sometimes be easier than balancing from scratch, but also sometimes it can be more difficult from balancing from scratch. Okay, I'll show by changes in oxidation number first. These are our 2 redox changes because the hydrogen is remain as hydrogen plus 1, the oxygen remains as oxygen minus 2 in each of these. It's the same here. Only the copper and the nitrogen has changed, but remember the nitrogen hasn't changed in forming this, but it has changed in forming that. So we focus on the 2 things that has changed. This is called lowest common multiple. Primary school mathematics, at least it was when I was in school. So lowest common multiple, the LCM equal to 2 times 3, which is 6. To go from plus 2, you need to reach 6. You need to multiply by 3. So that means R is equal to 3, right? Because I want to have 3 of these in order to give me 3 times plus 2. It must be balanced by minus 6. So 3 to go to 6 will be multiplied by 2. So I need to have 2 of the NO, so that I have 2 times N plus 2. All right. Now, when you think about you have 3 nitrate, 3 times 2 nitrate, there's 6 nitrate. You might think this is 6, but that is actually incorrect because the nitrate doesn't undergo redox in forming this nitrate, but some of the nitrogen actually forms this. So altogether you have 3 times 2, which is 6 nitrogen, plus 2 nitrogen, you have 8 nitrogen. You have 3 copper and no other copper, so you have 3 copper there. And of course now you have 8 hydrogen, so you will have 4 H2O. That will give you 8 hydrogen. To give you 4 oxygen plus 2 oxygen, there's 6 oxygen. And 6 oxygen. So 8 of the, is the oxygen balance? Let me have a look. So you have 6 nitrate here, 3 times 2, so you have 6 nitrate. You have 8 nitrate, so you have 2 extra nitrate. 2 extra nitrate will mean 2 times 3, which is 6 oxygen, 4 oxygen, 2 oxygen, 4 plus 2, 6 oxygen. Okay, so that is just using changes in oxidation number to balance this redox equation. Of course, you can try and balance it from scratch. It might just take you a bit longer, but it will not be impossible. All right, so sometimes one method works out easier than the other. Sometimes the other way around. So you should be capable of both anyway. Okay. So number 5, what's the electronic configuration of an isolated nickel 2+ ion? We start from nickel, for example. there's argon, there's your 4s2, so potassium and calcium. Go across your 3D and you get 3d8 because you're in group 10. So you got 4s2 and then 3d8 to reach to nickel. When you have nickel plus, you feel 4s before 3d for the atom, but you also lose from 4s before 3d. So there's nickel plus, you want nickel 2 plus, you will lose one more from the 4s, and now you're left with 3d8. The argon is just 1s2, 2s2, 2p6, 3s2, 3p6, 3d8. So there's no 4s and it's just 3d8. So D is our answer here. Number 6. So we know that AlCl3 is your period 3 chloride. So in actuality, we define or we think of the structure of AlCl3 as a giant ionic, but with a great amount of covalency, with a great deal or great amount of covalency. And this is a result of very small, highly charged Al3+, which is very polarizing. Okay, it polarizes the anion a lot, and this results in a huge amount of covalent character. So when you hit them, they can form Al2CO6, and Al2CO6 is exclusively simple molecular. So there's a change in structure and bonding. So I always like to draw a display formula like this, and then I remember that, AlCl3, aluminium only has 3 outer shell electrons, so this must mean that one of them is not a common covalent bond. Unlike these other 3, this is a dative covalent bond, just like this. So this is a dimeric species here, and sometimes question can ask you, count how many lone pairs there are. So these things are used for covalent bonding. For dative covalent bonding, they are not considered your lone pair anymore, alright? As a result of this dative covalent bond aluminium, you are also not 120 degree anymore, you are 109 degree. Okay, so which bonding is present in Al2Cl6? So you do have covalent, you do have dative covalent, but you do not have ionic, okay, because now these are simple molecular exclusively. You don't just have covalent, you also have this dative covalent bond. These are your case study as part of chlorides of third period element, as well as something you have done when you first did dative covalent bonding under structure and bonding. Number 7, you're looking for the smallest angle. So BH3, you can relate it to your case study, which is BF3. This is all under valence shell electron pair repulsion theory. A lot of students said they don't even know about this VSEPR thing. It's called valence shell, outermost shell, electron pair repulsion. When we count the number of bond pair and lone pair, we need to consider how do they repel, alright? There's 3 bond pair and 0 lone pair. Boron is in group 13, it's got 3 outer shell electrons. You use up everything for bonding. So there's your trigonal planar, 120 degree. And you said that BH3 is not in your specification, but BF3 is specified under structure and bonding as part of VSEPR. Okay, learn how to relate, and you should be alright. CH4 is your classic tetrahedral because, well, it's part of your organic chemistry. I hope you know there's your 109 degree, carbon sp3 with 4 bond pair and 0 lone pair. As you could see, 1, 2, 3, 4, there are 4 sigma bond, so 4 bond pair. Carbon is in group 14, uses 1, 2, 3, 4 for bonding, normal lone pair. So the 4 bond pair repel equally, and you get tetrahedral carbon sp3. This is C2H6. I wouldn't necessarily, maybe I'll draw it out. I'm running out of space here. So this is your classic alkene chemistry. There's a 120 degree. You don't count the pi bond as a sigma, so there's just 1 sigma, 2 sigma, and 3 sigma around each of the carbon. Same deal here, 1, 2, 3 sigma, but there's actually 0 lone pair because the carbon actually uses all 4 of its outer shell electrons to form covalent bond, including 1 pi bond there. 3 bond pair, 0 lone pair, same as that, 120 degree. NH3 is another classic one. See, I'm running out of space here. Maybe I just draw here. You gotta show the 3-dimensional geometry where you still have a lone pair on the nitrogen. Because the nitrogen is in group 15, it uses 1, 2, 3 for bonding. It still has 1 lone pair. And because we're talking about electron pair repulsion theory, you have 1 lone pair bond pair, repel more than your bond pair, you get 107 degree trigonal pyramidal. So among all these, the smallest one have to be the ammonia with 107 degree, smaller than 109, smaller than 120 degree. As a result of this presence of lone pair that repel, well, lone pair, bond pair repel more than bond pair. That's why this is called electron pair repulsion theory, and you are expected to explain it in terms of this in your theory paper. Okay, in next bit, you have a sample of pure gas, you put into a gas syringe, you have this temperature, you have this pressure. You compress the gas, so you apply pressure, and then the volume become half as usual. As you expect, when you apply pressure, the gaseous molecule get closer together and they occupy lesser volume. After compression, the temperature of the gas in the syringe increases. After you compress it, the temperature increases and the pressure also increases because you're under higher pressure. That's why your volume is half, alright? So it's asking which statement is correct. Intermolecular forces between the gas molecules are significant. So if you have that, if they are significant, then the gas will behave non-ideally. And it's possible to calculate the number of moles present using this data alone. Which statement is correct? So let's think about before and after. So initial or before. T equal to 300 Kelvin, pressure equal to 16 times 10 or 16,000, I can write it. Pascal, let's say your volume is equal to V initial, VI. So I don't know the actual volume because they don't give us. And then they say after the temperature is 375 Kelvin, the pressure is now 40,000 Pascal, and the volume final is equal to half the volume initial. So they don't tell us. Okay, maybe I just use half V and then I just say initial volume is V, then the final volume is half. So we are not given the exact value of the volume. So even when you want to use PV equal to nRT, you know T, R is a constant, you know P, but you don't know V. Then how can you work out N? This is one equation. You have two unknowns because they don't provide us with a volume. So it is not possible to calculate the number of mole given this data alone because you don't know the value, the absolute value of volume. So I can tell you B is incorrect. How do we check for ideal gas behavior? So this is the ideal gas equation, right? So that is the ideal gas equation. So we are not taking out the sample at all. So N will be constant, R will be constant. So PV over T equal to NR, and NR equal to constant because we are not adding in more gas. We are not taking out the gas. The molar gas constant is constant. So PV over T is constant. Let me work out PV over T. So that is your P times V, which is 16,000 divided by 300. So that is 53.3 V. Expressed in terms of V, I just do 16,000 times V divided by 300. And here, the PV over T will be 40,000 divided by 375. And I get, oops, hang on. But you also have the half, so you gotta put the half in as well. So PV over T equal to 40,000 times a half V over 375. So the V is the variable, the V is the expression which you don't know, but it's got a half, so times half divided by 375. And I also get 53.3 V. So you can see they are the same. So PV over T hasn't changed from the initial condition to the final condition. So this is an ideal behavior, okay? Because PV over T initial is equal to PV over T final, as I've shown you that. So they are behaving ideally. When you say the intermolecular force between them are significant, you are saying that they are not behaving ideally, but they are behaving ideally. All right. You say the pressure are too high for ideal gas behavior, but they are behaving ideally even under that high pressure. So, you can't say that they are not ideal. A and D are saying that they are not ideal. C is saying that they are ideal. The calculations show that they are ideal. All right. Next question. So we have calorimetry. A bit confusing here because only 45% of the energy released is absorbed. So we have 1.60 gram of a fuel. We want the energy released per gram of fuel, not per mole of fuel, per gram of fuel, because they don't tell you what is the fuel. Okay, you don't have the molecular formula of the fuel. This is the heat energy given out to the water. It's MC delta T that exclusively belong to the water, which is the solution. So 200 gram of water multiplied by your heat capacity given in your data booklet, joule per gram per Kelvin. Temperature difference, so delta T is temperature difference. Delta T in Kelvin is equal to delta T in degrees Celsius, because these are not absolute temperature. These are just temperature differences, all right? So 66.0 minus 18.0, get 200 times 4.18 times 66 minus 18, and you get 4128 joule. Gram and per gram cancel. Kelvin, because these are temperature difference, so whether they're in degrees Celsius or Kelvin doesn't matter, they cancel. But you need to remember that what you receive from the reaction, this is only 45%, because only 45% gets to the water, all right? So only 45% is 4128 joule. So therefore 100% from the fuel is going to be the direct proportion. So that times 100 divided by 40, I get 100,320 joule. All of these are expressed in joule, so I'll leave my answer in joule. But then that is for 1.60 gram of fuel. I want it per gram of fuel. So therefore, per gram of fuel, 100,320 joule divided by 1.60 gram of fuel. This is of the fuel, and I guess 62,700 joule per gram, and they want it to 3 significant figure. Have I done this correctly? Why is none of the answer given there? Let me just double check my working again. So 66 minus 18 times 4.18 times 200, that's 4128. 45% release is absorbed by that much water. So that much times 100 divided by, I know, you see I used 40, should have been 45. So this was a very, very careless mistake, and something that you can avoid if you are being more careful, not careless like me. But thankfully this is a multiple choice question, so I get to find out that my answer was not correct, okay? But you might not get that chance in a practical paper or in a theory paper, okay? So it's 55,733, and to 3 significant figure is 700 joule per gram. Okay, so they already said per gram there, that's why they don't have per gram there, but I mean that's just bookkeeping, yeah? So yeah, okay.